Hello and welcome back to the second quarter of Survey of Biology. And to start off this quarter, we're going to have a discussion of energy and enzymes. And we just wrapped up with biomolecules and nutrients. So this segues in really nicely because proteins are what make up enzymes. And enzymes help in digestion, which give us energy. And biologically speaking, that's what we need to stay alive. So what is energy? Energy is just the ability to do work. Okay? And in terms of biological systems, that can be mechanical work, so that's movement. Think of our muscles. We can have transport work, so the cell membrane and the transport proteins working there. And then finally, chemical work. So when we talk about photosynthesis and respiration and ATP, excuse me, we'll be talking a lot about the chemical work involved. So what are the forms of energy? Well, the two main forms of energy that we have are potential and kinetic. Now, potential energy we can think of as like a battery. It's stored energy or energy of position. So if you were at the top of a slide on the playground, you've got lots of potential energy. And the opposite of that is kinetic, which is the energy of motion. So as you slide down the slide, you're releasing kinetic energy. So the motion of waves, electrons, atoms, molecules, and substances. So those are the two main breakups of energy that we're going to see. And within those, we can get more specific. And again, let's just kind of go through. So potential energy, we've got a battery, stored energy. Gasoline would be potential energy. If you have it in a container or in your gas tank, it has the potential to do work. Kinetic energy would be the motion of a car. Okay, and you can think up of many other examples if you want, but here's a few of them. And here's an example of a baseball. If we were to throw a baseball straight up in the air and watch it, its maximum potential energy would be here at the top of its flight because it has the most ability to fall back to Earth due to gravity, and it's got its minimum kinetic energy because it's not moving at that one point. And the maximum kinetic energy would be down here as it's moving. So as it almost hits the ground, it could release that energy into the ground. Now, some specific forms of those energy, and you can probably think of a lot of these, there's 7 main ones. And the first is mechanical energy, okay? And it can be potential or it could be kinetic, but that's the energy of motion. There is sound energy or wave motion, okay? So the echolocation that bats and porpoises use. There's chemical energy, and this is going to be a big one for us because ATP, glucose, the sugars, carbohydrates all fall into this. Gasoline is a form of chemical energy. There's electrical energy. There's light or radiant energy. Heat or thermal, we'll talk about this one a lot because we all lose energy as body heat. This is a low quality energy because we really can't trap it in a lot of it in terms of body heat. And then finally there's nuclear energy. So these are all specific forms of energy, and in each one we could find examples of potential versus kinetic. So again, the forms of energy, and you should write these down in your notes as you follow along. So we've got solar, chemical, nuclear, sound energy, which is wave motion, mechanical. Now some people will say, well, isn't wind a form of energy? Well, wind would fall under mechanical because it spins the turbines that would generate the electrical energy, which is the next one. And finally, we've got thermal or heat energy. So these are the forms of energy that you should be familiar with. And the great thing about energy is we can have all sorts of energy transformations. So we can have chemical in the form of sugars and ice cream to mechanical energy to be able to ride a bike or run or play soccer or whatever it is. We can have radiant or light energy be converted to chemical energy through photosynthesis. We can have chemical energy in the form of gas be transferred to mechanical or kinetic energy in the form of a car moving. And we can have electrical energy be converted to thermal energy every time we use our oven. unless it's gas, and that would be chemical to thermal. But you can see there's energy transformations between all the different forms of energy that we have into other forms that might be more useful for us. And that leads us to the laws of thermodynamics. So the first law of thermodynamics say that it is the conservation of energy. Okay? Energy cannot be created or destroyed. We've got to account for all the energy that we have. Energy can be transformed, but it must be conserved. So we can transfer or transform energy from chemical to mechanical, from electrical to thermal. But we've got to account for all of that energy somewhere. It may be transformed into different varieties. Like if we burn a gallon of gas in a car, some of that energy goes into heat, some of it goes into motion, some of it goes into sound. But if we sum up or add up all those forms of energy, it has to equal the amount of chemical energy that was in that original gallon of gas. So the first law of thermodynamics says that energy cannot be created or destroyed. And here's a diagram of balance that shows that. So the energy before has to equal the energy after. Even though energy transformations can take place and it may look different after, they have to be equal before and after, and that's the first law of thermodynamics. The second law of thermodynamics is one of my favorites, and it encompasses this idea of entropy. And basically what it says is that the entropy, the simplicity, increases in a closed system. So unless we add energy, things will tend towards disorder. They will go from being very ordered, in this diagram here, to less ordered over here on the right. And that's the idea of entropy. So the second law of thermodynamics says that each energy transfer or transformation reduces the energy available to do work. So we end up with less usable energy. And then finally, here's the big one. It says systems will tend towards disorder unless energy is added. And that's the idea of entropy. And the reason why I love it so much is I always think of my college dorm room, because I never put energy into picking it up, and it quickly tended towards disorder, and it was always a mess. So some of you know people like that. Some of you may be a person like that. And that's the idea of entropy, is that systems will always tend towards disorder. Here, body is a biological system with the same thing. Unless we put energy into the system in the form of food, we will start to break down and eventually die. We will tend towards disorder. Here's an example of entropy with water. So delta S is the symbol for entropy. And as a block of ice melts, the entropy increases. It becomes more disordered. Okay? And if you look down in the lower right here, here is an ice crystal, which is very ordered. It's arranged in a pattern. And as it warms up, as it melts, it becomes less ordered. The entropy has increased. So unless we put energy into the system, in this case, in order to keep it cool, then things will tend towards disorder. It becomes less ordered. And so to wrap that up, here's a little cartoon. It says, Mom, you can't fight the second law of thermodynamics. All things, which includes bedrooms, move from a state of order to disorder. So it's very hard to keep things picked up biologically or in your bedroom or in my classroom. As you look around, you can see that there tends to be quite a bit of entropy in my classroom. So thanks for your attention, and we will talk with you soon.